Okay, we are recording. Thank you for the reminder. Okay. Okay, now I'm going to make one quick comment about tests. So the first test will be posted on Monday, September 21st. And it'll be due sometime later that week. So there'll be a window of time during which you can take it. But certain specifics I've not yet determined, such as how much time will be allotted for it, how many problems will be on it, and so forth. I can tell you that it will cover material from the homeworks up to that point, which is basically anything being covered in Chapter 1. So we have a couple sections this week, and then a little more after that. Of course, next Monday is Labor Day, so we won't have a class meeting then. So the other thing I'll point out is I've seen how in certain homework problems that there are certain annoyances in them. For example, in addition to answering the actual question, they'll have you enter a matrix in reduced echelon form, when actually the question can be answered without going to that trouble. So basically, I'm going to be taking all the problems you've been given for homework, and I'm going to take a subset of those and make the test from there. So depending on which questions I feel are best to put on a test, and of course there's an inherently limited selection of I'll have a decent amount to choose from, but it's possible that I may need to modify the directions for the problems in the test, so compared to what it says in my labs. So if I end up having to do that, hopefully I will not need to, but if so, I just want to give you a heads up now, but that's something I may do. Regardless, your score when you take it in my labs is not the final score that you will get for the test, because number one, I will review all tests myself, so I can give partial credit. And then after I've graded everybody's test, reviewed for partial credit, depending on the class performance, tests might be curved. So only then will you know the score. So what do you have for what do you see in my labs when you take it, that you can think of it as a lower bound? So it can only go up from there, not down. And I would try to have those handled as soon as possible after the test is due. So so if I need to modify the instructions a little bit, like for example, here's this problem, but don't do this part, I will let you know. But it's important that you keep that in mind when you take a test. So I'm giving this heads up now. Okay. All right. So when I have more information about the test, there will be a practice test after I make a real test. So sometime like within a couple weeks or so, I'll have that posted so you can get ideas to what sort of things you need to do. Another thing I want to make clear, since I've been getting questions about this in my other class. So unless something changes, unless there's some announcement by President Bennett, certain classes will start meeting face-to-face next week, right after Labor Day, September 8th. This class will not be one of them. So all of my classes are online from start to finish. I didn't want to have some chaotic change in format midway through. But some of you may be in a position, like maybe one of your other classes is going to start meeting face-to-face next week. So faculty have been asked to remind students about USM's health protocols. So if you go visit any page on USM site, there'll be a link to all information about coronavirus. The health protocols are supposed to be given in every class syllabus. Be sure to check those. We had a situation where some students who, based on their major, really should have known better, had come into close contact with someone who had tested positive, and they didn't bother informing the Moffitt Health Center. It's these kind of breakdowns that lead to more cases and just lead to more trouble all the way around. So, please familiarize yourself with USM's health protocols, and please follow them, especially if you are in a situation of taking at least some classes, besides this one, face to face. Okay. Okay. Yeah. So, in one of the documents that's posted, there's a link to the main page on Canvas, has the schedule. Now, but the schedule right now says September 21st, test 1 due. That is not accurate. I need to fix that. That's when test 1 will begin. That's when it'll be posted. It'll be due a few days after that. Okay. So we have a little more than, we have 3 weeks until you'll start working on that. Okay. So now I'm going to get my screen shared here. Okay. So in continuation of our exhaustive study of systems of linear equations, the focus for today is exclusively on systems of equations like this one that have one thing in common, that the right-hand side values are all 0. Now, to get a solution of a system of equations like this, it's very easy to get one solution in particular, and that's just by setting all the x's equal to 0. But in many cases, that's not the only solution. So we want to be able to describe all possible solutions of this kind of system. So that's what, and that would be called a solution set. So we want to be able to describe, for a system like this, the set of all possible solutions. So what I need to do first is establish some terminology. Dang it. Okay. So first, so when we have a system like this where the right-hand side is 0, that's called a homogeneous system of linear equations. Homogeneous is one of the most, or maybe the most overused word in mathematics, because it's meant to describe a number of different things that aren't all necessarily consistent with each other. One place where it's often used is when you have some kind of equation where it's a system like this, or also used in differential equations, where you have a right-hand side and when that right-hand side is 0. It's something that comes up in several classes. I want to make you aware of that. So what do we know about a homogeneous system? So as I mentioned earlier, you can always solve it by setting all of your unknowns equal to 0. So that's called the trivial solution, is the 0 vector. So we want to know, given a system like this, when is there a non-trivial solution? So is there a set of non-zero x values that will still give you 0 on the right-hand side when you plug them in? So the answer is, if you row reduce this matrix, like down to echelon form, and if it has any free variables, then there's a non-trivial solution. So another way of saying it is, once you row reduce it and you identify your pivot positions, if every column has a pivot position, you only have a trivial solution. But if there's one column that does not, again, column, not row, if there's one column that does not have a pivot position in it, then you know that there is a non-trivial solution. So what I'll do here is perform row operations on this system and see what we get. So we go ahead and add the first two equations together. Okay. And eliminate that term, and then take twice this row, subtract it from the next. Okay. And what we can see right here, and yes, a lot of problems in the homework and in my labs are contrived this way, that these two rows are simply negatives of each other. So what that means is you can tell that if you add them together, the third row is just going to go away. Okay. So we end up with 0 equals 0. So this third equation now we can ignore. So if we were to think of this as a matrix, 4, minus 2, 10 in the first row, and minus 8 and 6 in the second row, this 4 and this minus 8, those would be our pivot positions. So in the row 1, column 1, row 2, column 2. The third column has no pivot position because we don't have a non-zero entry down here. If we did have a non-zero entry here, then yes, the third column would have a pivot position. So it follows that x3 is our one and only free variable. But because there is a free variable at all, we know that there is a non-trivial solution. So to find out if there is a non-trivial solution, that's all you do. Row reduce, find out where the pivot positions are. If there's a column that doesn't have any, yes, there's a non-trivial solution. A little later, we're going to see, okay, once you know that there is a non-trivial solution, how do you actually get it? So we'll be able to do that too. All right. So now we'll try the same thing on this system. So, so again with row operations. So what row operations should we perform to try to get this into echelon form? Anyone? Go ahead. Sorry, could you repeat, please? Oh, that's weird. Okay. If you want to type it into the chat. Almost. slight mistake in that. Yes, that. Yeah, because they have opposite signs, we had to add. So, okay, great. So now we have row 2 is itself plus 4R1. And that's eliminated. Here, it's clear what to do. We just subtract the rows on this next one. Okay. And now we see that here it's clear what the next row operation will be. We're just going to add these two to eliminate this element. Unlike the last problem, okay. Hold on, I'm catching some background noise from somewhere. Okay, that's weird. Unlike the last example, these two rows are not multiples of each other. So that tells us that when you eliminate this 5x2 down here, just by adding the rows together, that we will have something left over right here. So by contrast to the last problem, every column has a pivot position. So 1, 1, 2, 2, 3, 3. So in that case, there is a trivial solution. So those are the different kinds of outcomes that you can have when it comes to this kind of homogeneous system and you're forming row operations just to get it to echelon form. Speaking of echelon forms, because we have echelon form and then there's also reduced echelon form. And I come from the numerical linear algebra world where we we write code to have these kind of systems solved. And we have software such as MATLAB doing the work and certain algorithms there that are very similar to what's taught in a class like this one. But in that kind of setting, we actually have really no use whatsoever for reduced echelon form. Just getting to echelon form is enough. And that's why I've been focusing on that. Let's see, I see a question in the class. Will this class be on ground after Labor Day? So no, as I mentioned earlier, this class is online whole semester. We are not changing format. Back during the summer, we were making a schedule and determining which classes would be face-to-face, which would be online, and as faculty we could request whether we wanted a class to be face-to-face, but there had to be a good reason. Like for instance, certain classes it's very important to have an in-person component, such as a lab. And I decided I didn't want to mess with that because I figured we'd probably have to change format anyway. So I didn't want the chaos of a transition. Okay. So now that we see how to tell whether a system of equations, a homogeneous system of equations, has a non-trivial solution or not, the question now is, how do we, if it does have a non-trivial solution, how do we get it? So here we have this system, and we need to again get to echelon form. So here we have a 3 times row 1 to be added to row 2 to get rid of that minus 6x1. And what happens is that the last row ends up being wiped out entirely, just because if you look closely, the second row here is just minus 3 times the first row. So these equations are actually saying exactly the same thing. The second equation is redundant, and sure enough, the row operation reveals that. So we have a row of entirely zeros. I just want to move all 0 rows to the bottom. So we're just going to swap there. Okay. So now we can see that we do have a free variable. Anytime you have a row of zeros like this, when it's a square system, so free equations, free unknowns, if any of those rows are zero, there's going to be a non-trivial solution. So the third column does not have a pivot position. We only have them in 1, 1, and 1, 2. So we have this free variable x3. So now what we need to do is solve for the other unknowns, x1 and x2, in terms of x3. So we're just going to go to these equations and get those solutions. And what you do is you move from right to left. So we're going to get x2 first, because here we see that x2 depends only on x3. So here we just go to this equation and rearrange it to get x2. So x2 turns out to be 2x3. And then I need to take this equation and rearrange it to solve for x1. Now notice there's two steps involved here. This first one is just a rearrangement. So I'm just rearranging it to isolate x1. Now I have this expression in terms of x2 and x3. But I already know x2. So I have to substitute that for x2, and that's what we have here. So then you work all this out, and we wind up with minus 4x3. So x1 and x2, those are your non-free, also known as basic variables. So we need to solve for these and get expressions that are only in terms of free variables. That's something it'll always be possible to do. So by solving for x2 first, that helps me get an expression for x1 in terms of only x3. So questions about the solution process before I describe how the solution is to be written. Okay, so now we're going to if we go back to the beginning of the question. It says write solution set in parametric vector form. So you're going to see what that means now. So what I have here is my formulas for x1, x2, x3. So x3 is just a free variable, so that's just plain old x3. But notice, because everything depends on x3, it's something that we can factor out. So I go ahead and do that. Now it's in parametric form. So this is what your final answer would look like. So any free variables are outside, and then we have only numeric coefficients inside. So what this is saying is every non-trivial solution of this system has this form. It's some value for x3, because remember, x3 is a free variable. You can set it to any number you want. So then x3, whatever you choose, times this vector is a solution of a system. All right. So now we'll do the same thing with this system. Now what's nice is there's actually no need to perform row operations. This matrix is already in echelon form. So that was unusually generous of my labs to actually give you that start. Now, let's take a look at our pivot positions. We have it in column 1. There's a 1, 1 position, and then also in a 2, 2 position. So because here are pivot positions, the other two unknowns, so we have 4 unknowns altogether, x3 and x4, are your free variables. So whereas this problem, the solution set is one-dimensional, there's only one free variable, this one is going to be two-dimensional. So to summarize, so x1 and x2, those are the ones that are not free. So there are different terms for them. I've seen them called pivot variables in some books. You'll see them referred to in my labs as basic variables. So you're always going to be solving for your basic variables, x1 and x2 in this case, in terms of your free variables, which in this case are x3 and x4. So now what you can do is you can take this equation and solve it for x1 and x2 in terms of x3 and x4. Now, I'm going to write it out so you can see what's going on here as an actual system of equations. Now, this is something you don't need to do, but it might help you learn a process so that in the future you can try it directly on this matrix without having to write it this way. So this helps you see what the process is. So what I would do here is I would take this equation and solve it for x2 just by rearranging. Then I would solve this one for x1, again by rearranging, but also you take your value of x2 that you got from down here and you substitute it in here. And this is actually called back substitution just because you're going through the equations in reverse order, so from the bottom up. So you solve, substitute, solve, substitute. You keep going until all the basic variables are known. So if we go ahead and solve the first equation, it's what we work on first, but it's the second equation that's written. x2 turns out to be this, and so it's in terms of x3 and x4. So x2 is done. So now I do the same thing with x1. I move these to the other side, and I have this. But I'm not done because I need everything to be in terms of only x3 and x4. Therefore, I have to take my previous expression for x2 and substitute it in here. And that's what gives me this. So now everything is in terms of x3 and x4, but I need to simplify it. So I have some like terms that I need to combine. And once I do that, then this is what I have in terms of only x3 and x4. All right, so same thing as in the previous problem. It's just that this time we have more free variables to work with than before. So now I can describe the solution set. Okay. So let's focus on this first. Actually, I want to move the rest down. Okay. This is not getting in the way. All right, so all I did here was I took my formula for x1, my formula for x2, and put them in here for first and second spots, and then x3 and x4 are a free variable, so you just put in x3 and x4. Now, in this case, we have two free variables. So what you do is we need to separate this into a sum of two vectors. One that has only x3 and the other that is only x4. So I gather all the x3 terms and put them in a vector. So like in this last spot, there's 0 because there is no x3 here. And then I have a second vector that has all the x4 terms. So in the third position, there isn't any x4, so again, there would just be 0. Now, in the last problem, I had a bunch of x3, so I factored them out. Here too, in each of these vectors individually, I'm going to factor something out. Factor out x3 in this one, x4 in this one. Now we're done. So this is a solution set in parametric form that you can choose any values you want for x3 and x4, multiply those chosen values by these vectors, respectively, and that describes all possible solutions of this system. Now, one thing that these all have in common is that in each one of these vectors, one of your free variables is going to have a 1. All others will have a 0. So we see that here. So here we have only x3. Here we have only x4. And then the other elements will come from when you're solving for your basic variables in terms of your free ones. So however many free variables you have, that's how many terms you're going to have, how many vectors you're going to have in your solution set. So now this next one will play out the same way because it's already in echelon form and it has these two pivot positions. So once again, we have these two free variables, x3 and x4. So we're going to, again, solve for x1 and x2 in terms of your two free variables. So here, we'll do this without having the system of equations. So here we have, this is x2 plus 3x3 minus 7x4 is 0. So if I show you the formula for x2 in terms of x3 and x4, look at the coefficients, minus 3 and 7. They have a negation of what you have here. Why? Because these terms were moved to the other side to isolate x2. So you're always going to have that, a negation of these coefficients. Now, here, my coefficient is 1. So I only need to negate these. But if I had something else here, like 2, I'd have to, whatever coefficient I have here, must divide by. So now for x1, same thing. Whatever coefficient, so this is a coefficient of x1. I'm going to take all of these and negate them to get an expression for x1. Here I have minus 3, minus 7, and 3. So I have the negations of those right here. So that starts out my expression for x1. But now x2 is not a free variable. Any non-free variables you have, you must substitute. So we put that in here. And then distribute and combine all the like terms. And this is what you get in the end. So you're solving for one of your basic variables, take your other coefficients, negate, and if necessary, divide. It just wasn't necessary in this case. So now we do the same kind of separation as before. So if we look at the terms involving x3, so if we look at our basic variables, for x1, I have a coefficient of minus 2. For x2, I have a coefficient of minus 3, and that goes here. For x3 in the third position, I just have a 1. There is no x4, or sorry, there is no x3 in the formula for x4 because x4 is also a free variable. So that's why we put 0 in this case. And then we add on the terms for x4. Again, look at the coefficients of x4 in all of your formulas. For x1, it's 18. For x2, it's 7. For x3, we don't have anything. So it's a free variable. And then x4, it would just be itself, so it's 1. So this is how you get to the final form of a parametric solution a little more directly than I did in the previous problem. But at least in the previous problem, you can see the process, but you can read off the coefficients to see what should go in these vectors right here. So you don't have to go through this whole process like I did here of writing it out like this, but you can see where these coefficients come from. So questions about this process of writing down formulas for a solution set like this one. Now, these next couple, the matrix involved is not already in echelon form. So there is a little illumination that needs to be done. Now, normally what we do when we go for these systems is we look at the ratio of elements and figure out what multiple of this row to subtract from this row and so forth. But sometimes, especially when we have integers, it can be helpful to do some scaling first, because this kind of row operation, when you take a multiple of this row and subtract from this row, it's easier if the entry you have here is a 1. So sometimes it's a good idea to scale it so that this entry is 1, or maybe rearrange rows to get a 1 up here. So that's that's something that's perfectly fine to do. Certainly can cut down on mistakes. So in this case, I notice that every element of this row is a multiple of 4. So I'm going to divide by 4. And let's see what we get. And well, what we have here is these rows are just negatives of one another. So as soon as I add them, this second row is going to be wiped out. Okay, so now we just have this. We only have one pivot position in the whole matrix. It's this one right here. So x1 is our basic variable, and x2 and x3 are free variables. So now we just have one equation to work with to solve for x1 in terms of x2 and x3. So reading it off a matrix, I want to say x1 is equal to a constant times x2 plus another constant times x3. Can anyone tell me what it would be? You can type in the chat if you prefer.
Sir, can you repeat the question?
Okay. What I'm looking for is x1, you're solving for x1, equals a number times x2 plus a number times x3. So I'm looking for an answer of that form. So what would those numbers be? Okay. Yes, x1 is okay. Yes, it's 2x2 minus, yes, Whitney, yes, it equals. I figured that's what you meant. Depend, yes, both the answers are correct. So very good. X1 is 2x2 minus 5x3. We take these values and negate them. Since this coefficient over here is 1, there's no need to divide by anything. Okay, so now we have that. Okay, so now we have to describe this in parametric vector form. So here we have x2 times this coefficient, and then in its own position it would be 1, and then for the other free variable you'd have 0. Plus x3 times the coefficient of x3, it goes up here. For x2 there's nothing because that's a free variable, and then for itself it's 1. So remember, for free variables the coefficients are always 1 or 0. And we're done. That's the solution set. All right. Now, here, too, we have system of equations to, again, solve. But notice here again, the second row is just a multiple of a first row. So we go ahead and take the second row this time and divide it by 3. And now we see that the equations are identical. So we'll just wipe out that second row. Okay, so once again, we have just this equation to deal with. So what's interesting is we have one pivot position in the 1, 1 spot. So now we have x2, x3, and x4 are all free variables. x1 is the only one that we have to solve for. So we solve for it in terms of x2 and x4, again, by negating these coefficients. But then to get it in parametric vector form, you might think, well, for x3, there's nothing here. So you might think, oh, well, the solution doesn't depend on x3, but actually it does. And you'll see when I write out the parametric form. So for x2, we have this coefficient goes here. Then for itself, it's 1. And then the positions corresponding to the other free variables, x3 and x4, you get 0. Now the same thing actually applies for x3. There's no x3 here, so there's a 0 in this spot. And then there's a 1 in its own spot, and then for the other free variables, you again have 0. So this is still part of a solution set. So even though it doesn't appear here, it still appears in the solution set. Just times a vector that's nearly all 0. And then finally, for x4, we have as a coefficient of x4 goes up here. For the other free variables, you get 0. For itself, you get a 1. So notice we have 1, 0, 0, 0, 1, 0, 0, 0, 1 as the coefficients of your free variables in these three terms. So that illustrates more clearly than previous problems what the pattern is in terms of the coefficients of your free variables in your vectors. So one of them is equal to a 1, all others are equal to 0. And then for this row, the first row that has your only basic variable, these are the coefficients that go in these vectors. Yes, I made the shot. All right. Last one, we have a system of equations that has 4 equations of one of the rows is all 0. So basically, you might have a more complicated system of equations in this. If you do row reduction, and this is what happened, this is what resulted, this echelon form. And there are 6 columns. So there are 6 variables altogether. So I'm going to put this on a new page. So where are pivot positions? First row, we have this one. So in the 1, 1 position. So that corresponds to x1. Second row, I have in the third column. So row 2, column 3. And then the third row, it's all the way over here. So corresponding to x5. So x1, x3, x5. So in this case, the odd numbered variables are the ones that are basic variables. And then the other ones that don't have a pivot position, so column x2, x4, x6, those are your free variables. So now we have three of these three of the basic variables to solve for in terms of the free variables. So it's the same idea in terms of what you do with these coefficients. So we're going to solve for x5 first, then use that to help us get x3, then use those to help us get x1. So we're going to work our way from a bottom up. So what we need is, like, all of these correspond to equations where it's set equal to 0 on the right side. So I need to take this equation and solve for x5 in terms of x6. So from this, so remember it's equal to 0, what is x5 equal to in terms of x6? Yes. So we take this 5 and negate it. So x5 is equal to minus x6. Okay. And then similar over here, we take this coefficient and negate it. So x3 is also a multiple of x6 because there are no other non-zero coefficients in this row. So x3 and x5 both depend only on x6 by virtue of these non-zero coefficients here. Okay, so those are two of the three basic variables. We have one left. So what you would do is you would use these coefficients to express x1 in terms of x3, 4, 5, and 6. But then these expressions for x3 and x5 would have to be substituted into that. So what we get here would be, here's what you get just from negating a coefficient. So minus 3, plus 1, plus 4, plus 9. That's your starting point. But then these two get substituted in for any basic variables that are in this equation. And as long as you work your way from a bottom up, you'll always be able to find what you need. So then you just work this out and combine like terms, and this is what you get. So x1 depends on x4 and x6. Notice that nothing depends on x2 because that column is entirely zeros. But we saw something like that in a previous problem too. So now we can write out the solution set, and it'll involve three terms because we have three variables, x2, x4, x6. And each vector is going to have 6 elements because there's 6 unknowns altogether. So for x2, because there's nothing here in this column, there won't be anything here except for this 1 in its own position. And then for x4 only influences x1, it doesn't play any role of x3 and x5. So we see that that vector is mostly 0 too. So we have a coefficient of 1 for x1, and then for itself it has a coefficient of 1, but nothing else depends on x4, so there's nothing else here. And finally, for x6, we have a lot more going on. So we have a coefficient of x1 goes here. For itself, it is a coefficient of 1. And then for x5 and x3 are where we have the -5 and a -9. So there we have the parametric solution. Okay. So that's what this set is about. So you row reduce if necessary, which won't always be. Identify your basic variables and your free variables. So the basic variables are what are columns that have pivot positions, and all other ones are the free variables. And then you solve for the basic in terms of the free. That's what was done here. So then you can take whatever coefficients you have on your of your unknowns, and that's what gives you this parametric form. And remember, every free variable must show up in your parametric solution set. Even in a case like this, where it doesn't show up in any of these formulas here, in that case, that's where a column is all 0. You'll still have a vector like this that has a 1 in a position corresponding to its index. So here it's a 1 in the second position, and that's all you have. And questions about any of these or about other problems that you've been working on? Okay, I will end the recording at this point.